So your next kinematic equation is going to be your final x position is equal to your initial x position plus your initial velocity times time plus 1/2 of your acceleration times. You should be able to print it off class tomorrow and make sure I'm correct there. But I would hope you could print it off because my handwriting is not very good. So, but there's some things once we get into some more of the complex that use Greek, printing that off would be a little harder just because like alpha and A look so alike. And writing it and maybe putting a little note above it saying alpha would probably help. It's either positive or negative. Acceleration be 0. If a particle has a constant velocity of, say, 5 miles or 5 meters per second, then the acceleration is going to be 0 there because it's not either accelerating nor decelerating. C is 0. The acceleration does not have to be 0. An example of this is if you toss something up in the air, like a rock or a ball or something. At the peak, your velocity is going to be 0, but because it's an object in free fall, it's always going to have the constant acceleration of negative 9.8 meters per second squared. Does anybody have questions over anything so far? Okay. Okay, so if we have an object traveling eastward in the positive direction, can the acceleration be in the negative direction? So yes, whenever let's just make it more simple and say we're driving in the east direction. Anytime we slow down, our acceleration is going to be in the west direction. That's because there's a force acting on it in the opposite direction of the way we're going. Okay, on this one, as the points get closer and closer together, accelerating, because in that picture, we're assuming that the dots are taking pictures of a certain time intervals, say every second there's a picture taken. So as they get closer and closer together, the velocity is increasing. Does that make sense? So in this one, negative acceleration, meaning the dots are further apart. So as the dots get further and further apart, the slower they're going, meaning it's in a negative acceleration. So in this one, we don't see a change in speed. The dots are perfectly spaced apart, so there is no acceleration because velocity is constant. Your kinematic equation that is time independent means it does not rely on time. So your final velocity squared is equal to your initial velocity squared plus 2 times acceleration times the change in x or y, whichever equation you're using. This one, whenever you're looking for, say, delta x, whenever you're in search of that, but you're given both velocities and acceleration, but you're not given time, this is going to be a good equation to use, because otherwise you'd have to go into the first equation, get into second equation. But rather than doing that, you can just use one formula, take less faster. Yep. So meters is going to be our standard length or distance that we're going to use. I'm going to use the kilogram. I know chemistry, but physics, we're going to be using kilograms because we're looking at macro objects rather than micro objects like we do in chemistry. I'm going to use seconds. Right. Area units will be our meters squared. So meters cubed is going to be the units we're going to use for volume once we get to that portion of this. Once we get to momentum and inertia, but get to know the units now. So our velocity units are going to be meters per second. If you don't ever remember units from the equation and what you're doing can really help you figure that out. Your acceleration formula is velocity divided by time. So that'll be another handy equation to have. So velocity, distance over time. Acceleration, velocity over time. And now we're to our prefixes. So nano or lowercase n is going to be your -9 power, 10 to the -9th. If you ever have to convert from anything nano. Then we've got micro or lowercase mu is going to be 10 to the -6th. Then we got milli, 10 to the -3rd. Millimeter is going to be your most common use of this one because millimeter is 1 millimeter is 1 times 10 to the -3rd of a meter. Centimeter. 1 centimeter is 1 times 10 to the -2nd of a meter. Deci is 1 times 10 to the -1st. This one won't be used a whole lot. It might be used later in the semester, just kind of depending on the examples and problems he gives. So deca or decade, if you ever have a problem that says in 1 decade, you can know that's 10 years. Kilo, so any kilogram, kilometers, that all those are going to be 1 times 10 to the third of the measurement you're looking for. And we got mega, which is 1 times 10 to the 6th power. Tetras to the 12th. Now, how many centimeters are in 1 inch? Yes, 2.5 centimeters per inch. It's an important conversion. I'd probably write that down on your formula sheet just because come test time, you're liable to just go blank and you'll probably see that on your test. So whenever you're looking at kinematics in 2 dimensions, which quantities from the equations are going to remain constant, not change? So when we're looking at kinematics in 2 dimensions, our velocity x is not going to change throughout the entire problem. Because in this level of physics, we're looking at none of that. So if our velocity in the x direction isn't going to change, that means our acceleration in the x direction is going to be 0 as well. And our acceleration in the y direction is always going to be negative 9 meters per second squared. Like I just said, when we're looking at kinematics in 2 dimensions, our acceleration in the x direction is always going to be 0 because there's no resistance or wind pushing or pulling or anything like that. A projectile is considered a free-falling object because it does have gravity work component. So therefore it is free-falling just with an X component added to it. So acceleration in the y direction is negative 9.8 meters per second squared. Another constant that I'd probably put down just because once you learn it enough times, you don't have to memorize it because it's ingrained in your head. Just go through and eliminate wrong answers to get to the right one. So with the red one, its velocity is not zero, but the acceleration is zero. We know from the question when an object reaches its highest point, meaning it's in the air, it's a free falling object. So whenever we have a free falling object, the acceleration is never zero. So that takes out red and blue. And to get rid of green, its acceleration depends on the angle at which the ball was thrown. We know the acceleration is constant, so it's negative 9.8. So that gets rid of green as well, leaving us with yellow. Velocity is perpendicular to its acceleration. So as all of y'all figured out, it doesn't matter the weight of the object, that how fast it drops, because gravity is the same for every object and it doesn't rely on the mass. They hit at the same time. Good job, y'all. Yes, I'm going to post this, Alyssa. I'll post it later tonight and it'll be on y'all's on the website underneath y'all's section. Okay, if y'all will get checked in real quick, then we will get started on the worksheet. Okay, before we do get started on the worksheet, are there any questions so far about anything? Nothing? Physics is just clear for all of y'all? Okay. You're good. If there's no questions, let's get started. Can somebody on Zoom say something real quick? That way I can make sure we can hear y'all in here too.
Hello.
Awesome, thank you. Okay, so first thing we're gonna do is significant figures, just because it's really the first thing we learned, and I still struggle with significant figures sometimes, so it's always good to do a little practice before getting into the harder stuff. So how many significant figures is our answer gonna have on this first problem? Two. So we're gonna have two significant figures because we have two there, then we have four there. Whenever doing significant figures with multiplication, whichever one has the least amount of significant figures is going to be how many significant figures your answer has. So what does our answer wind up being? You get 6.32?
Yeah.
6.3. Okay. Easy enough. I don't know if he's going to give you just a simple significant figure. I know last year in the class I took, we had one or two. So those were easy problems. Get through them, move on to the next one. So now we have a house that is advertised as having 2,500 square foot. Now we're looking for the area in square meters. So our first step is draw your little picket fence. We got 2,500 foot times foot. Writing it out like that helps remind you that you've got to do two of everything to get the right answer. So now we know 1 foot is 12 inches. We do that twice. From there, we know how many centimeters is in 1 inch. 2.5 centimeters. Do that twice as well. And then how many centimeters in a meter? 100. Okay. Then you do that twice as well. So when we plug that in with the correct number of sig figs, we're going to say it has two, because with zeros, when it's alone like this, the two numbers in front of the two zeros are considered significant, whereas the following zeros are not, because there's not a decimal at the end. What'd you wind up with? Okay, 2 sig figs. 230 meters squared. Everybody on Zoom, understand that? Got that? Awesome. Okay, now a ladder is 8.34 meters long, leaning up against the side of a building. If the ladder is inclined at 68.5 degrees to the horizontal, what is a horizontal distance between the bottom of the ladder and the building? How far up the building is the ladder? What's our first step here? You can draw your triangle. So we know it is 8.34 meters long. We know the angle from the horizontal, meaning from the bottom, is going to be 68.5 degrees. What now? What equations are we going to use? Our SOHCAHTOAs. So we got sine of theta is equal to opposite over hypotenuse, and cosine of theta is equal to adjacent over hypotenuse. So now we can rearrange these. So hypotenuse times sine of theta is equal to our opposite. Our opposite is going to wind up being our y direction. And then we have h of cosine of theta is equal to our adjacent. And our adjacent is going to be our x. So now you can plug in 8.34 times sine of 68.5, 8.34. What do you wind up with for your y? Units. Yep. So we wind up with 7.76 meters. And then for your adjacent or your x, 3.06 meters. Any questions? Trigonometry, foundation. Another one. Vector has an x component of 37.8 and a y component of 67. Magnitude of the vector and the direction. So we're looking for theta and our r's. So we'll just go ahead and triangle, label it 37.8 and 67.5. Theta. What equations are we going to use here? So we'll use our TOA because tan of theta is equal to our opposite over adjacent. So theta is equal to our tangent inverse of opposite over adjacent. But how do we find r? Think back to pre-algebra. One of the first equations you learned. Pythagorean theorem. So we got our r squared is equal to our x squared plus y squared, which translates to r is equal to the square root x squared plus y squared. Yeah, I don't know how to spell it either. Pythagoras was a very complicated name. I don't know why his parents gave him that name, but so now just plug everything in. Once again, our y's are opposite and our x's are adjacent. This isn't necessarily always the case, depends on how you draw your triangle. So that's why I always refer to it as opposite and adjacent, because if you just learn that opposite's y and a's x, then it can throw you off. Like later on in this problem or in this worksheet, we'll have rain falling from the vertical. So our angle is going to be from the vertical. So our opposite and adjacent are going to switch. So we got 67.5, 37.8. Make sure your calculators are in degrees. And what is our theta?
Yep.
60.8 degrees. And our r is what? $77.4 meters. Easy enough. Any questions so far? Awesome. So now we have a ball being thrown straight up into the air. Starts out moving at 8.15 meters per second after falling 2.48 meters below its release point. I did change the distance it fell because whenever it was 6.48, like I have on the worksheet previously, you get an impossible answer. So I spent 30 minutes trying to work this problem out prior. So make that correction and you'll get a right answer. So what's the first thing we need to do? So first thing I like to do, I like to draw down. So we got somebody standing on a little something there, cliff maybe, I don't know for sure. Ball goes straight up and comes straight back down. We know it falls for 2.48 meters, hits the ground. So we know this distance is 2.48 meters. We know our initial velocity is 8.15 meters per second. No, not there. It's not our initial velocity. our final velocity down here is 8.15 meters per second. So now we write down what we know. We know our x initial is 0, our x final is 6.48 meters. And you could have your x initial as 6.48 and your x final at 0. It doesn't really matter because in physics, you get to set your own origin on this type of stuff. So kind of depends on just what you want. And then we're looking for initial velocity. 2.48. It's negative. So we're looking for initial velocity. Now our final velocity is 8.15 meters per second. What's going to be our acceleration? Negative 9.8 meters per second squared. So one thing else on the drawing, we know because gravity is constant that our velocity at this point is going to be the same as it is in this point, because it's going to either be slowed down or sped up the same because of gravity. So what equation are we going to use here? We have both x's, acceleration, and are looking for velocity. This will be so final velocity squared is equal to initial velocity squared plus 2 times acceleration times delta y. So our change in y is going to be that 2.48. So final velocity, we know is negative 2.48 squared. We're looking for initial velocity plus 2 times negative 9.8 times negative 6.48 minus 0. So now we multiply out. So 2.48 squared. You know that's 6.15 is equal to v naught squared. $27.008. Two. I was wondering why I was getting such a big number for that. Okay, that's better. So 48.608. Subtract that from both sides.
Wouldn't the V final be 8.15 instead of the negative 2.48?
Yes. Thank you. So that leaves us with 17.8145 is equal to our V naught squared. Then you do square root of both sides. Giving us what for our V naught? .22 meters per second. Any questions there? So now we got a graph. I kind of enjoy graphs. They're pretty simple. So here we have a position versus time. Because we do have a lot of material to cover, I didn't put all the times on here. I know if y'all go to the test prep under Lewis's section, you can see, you can get more practice there. And I do have the key available for y'all to go look at on there. So if you want to get more practice with the graph, y'all can do that. But since y'all have forces added on, unlike they do, I wanted to add a few force problems at the end. So what's going to be our equation to find velocity like we're looking for? Because we're looking for the average velocity. So our velocity equation is distance divided by time. Change in distance. So from 0 to 2 seconds, we stay at 10. So 10 minus 10 divided by 2 is equal to 0. So first 2 seconds, we went 0 meters per second. 0 to 4 seconds, because we are talking velocity and not speed, you just draw a straight line from the 2 times. So we started at, or we finished at 0 and started at 10, final minus initial. We went from 4 minus 0, giving us 10 over 4. That 10's negative, giving us what for our velocity? Two point five. Next, from 2 to 4 seconds, our final location was 0. Our initial was 10. Final time was 4. Initial time was 2, giving us negative 10 over 2, giving us a what for our speed? Negative 5. And then from 2 seconds to 6 seconds. So our final location, I'm going to call it negative 17. Minus our initial was 10. Final time was 6. Initial time was 2. So we wind up with negative 27 over 4. Giving us the velocity of what?
6.75.
Any questions there? Okay. Moving on to the next one, a train is traveling down a straight track at 22 meters per second when the engineer applies brakes, resulting in an acceleration of -1 meters per second squared. As long as the train is in motion, how far does the train move during a 20-second time interval starting at the instant brakes are applied? So we got a train going 22 meters per second, slowing down at 1 meters per second squared. It slows down for 20 seconds. So first thing I like to do, write down what you know. So we'll know V naught is 22 meters per second. We're looking for final velocity. We know our acceleration is -1 meters per second squared. We don't know our delta x. That's what we're looking for. And we know our time is 20 seconds. What equation are we going to use? What do we know? The x final is equal to x initial, right? Yeah. So x final is equal to x initial plus v naught t plus 1/2 at squared. So we can simply combine x final minus x initial to give us delta x is equal to v naught t plus 1/2 at squared. Now plugging in what we know, this is a simple plug-in problem. So 22 times 20 plus 1/2 times -1 times 20 squared. Which gives us what for an answer? Gives us 240 meters traveled. You ever feel like you're doing more English in here playing with letters than math? Yeah. You might learn another language too by the end of the semester. Yeah, like Greek. It's always nice to know. It'd be fun. Okay, now we have a brick is thrown upward from the top of a building at an angle of 32 degrees to the horizontal with initial speed of 12 meters per second. Brick is in flight for 4 seconds before hitting the ground. How tall is the building? So first thing we do, draw your picture. I was kind of mean on this one. I didn't give a whole lot of space for work. I don't think I realized how much work needed to be done. So I do apologize for that if you printed it out. Write small. So we got our little pedestal they're standing on the top of the building. Bottom of the building is the ground. They throw it. It lands somewhere over here. We don't care about where it lands. We know that angle is 32 degrees. We know initial speed is 12 meters per second. We know time is 4 seconds, so we write this down. Our V naught is 12 meters per second. What's our velocity in the x direction going to be? Cosine for x? Yep. So our x direction is going to be 12 cosine 32, meaning our y is going to be 12 sine 32. I just leave it like that and plug that into my calculator for velocity in that direction, just to get the exact value. So what's our acceleration in the y direction going to be? Negative 9.8 meters per second squared. X direction. I just like having zeros. Sometimes it simplifies things. We know our time is 4 seconds. And we're looking for our delta y. So what are we going to do now? Now that we know what we know and know what we don't, what equation are we going to use? So it's actually going to be the same one we just used, except in the y direction. So we're going to have our delta y is equal to our velocity in the y direction times time plus 1/2 a t squared. So we're looking for our delta y. We have our velocity in the y direction. We have time. We have our acceleration. So velocity in the y direction, when you put this in your calculator, put parentheses around it just to make sure it calculates first, is 12 sine 32 times 4 plus 1/2 times negative 9.8 times 4 squared. All that is equal to our delta y. Giving us what? $53 meters. Did you get a negative 53? Yeah. So you got that because we had our origin set up here. But so any questions thus far?
I actually had a question.
Yes.
What was the answer to the question before? I didn't see it.
240 meters.
Okay, thank you. And then for this one, you said something about why it would be negative, like why it's not negative. I just didn't hear it though.
Okay, so whenever you put it in your calculator, where the person is standing is where we have our origin set, just because that's where the angle's coming from. So because that is our origin, the brick is actually falling 53 meters below the origin, which is why we're getting a negative. But for the question, it's just asking how tall the building is. Obviously, a building can't be negative 53 meters below the ground and have something falling off the top of it.
Yeah, that makes sense. Thank you.
I guess technically it could, but that's kind of even more complicated than anything else. Any other questions? Awesome. So we got. So now we got a spitting cobra question. Anybody afraid of snakes? You don't like snakes either? Well, there's some weird people out there. I apologize if any of y'all on Zoom like snakes. I don't like them at all. So on this one, we have a spitting cobra can defend themselves by squeezing muscles around their venom glands to squirt venom at an attacker. Suppose the spitting cobra rears up from a height of 0.46 meters above the ground and launches venom at 3.7 meters per second, directed 41 degrees above the horizon. Neglect air resistance, find horizontal distance in M, traveled by the venom before it hits the ground. It's a wordy problem. So draw a picture, simplify it. So we have our ground here. Cobra rears up right there. 0.46 meters. Launches venom. It hits the ground. Launches from an angle of 41 degrees. Our V naught is equal to 3.7 meters per second. So now that we simplified it a little bit, write down what you know. So what's our V of X?
Cosine
What's before cosine?
3.7.
3.7 cosine 41. Then our V naught of Y is going to be 3.7 sine 41. Our change in Y is going to be that 0.46 meters. We're looking for our delta X. What's our acceleration in the Y direction? Acceleration in the X direction? Zero or negative zero. Okay, now that we know what we know what we don't, what do we do? What's next? This was one of the homework problems,
Well, something similar.
similar. It's a few steps long, so. First equation we'll use is our final velocity of y squared is equal to our initial velocity of y squared plus 2a delta y, right? So now we can plug in what we know. We know Vy is equal to the square root of 3.7 sine 41 squared plus 2 times negative 9.8 times negative, because our delta x is going to be negative, or delta y is going to be negative 0.46. Giving you what for your final velocity?
Would it be 3.9?
Yes, I believe so. Let me double check real quick. Yes, so 3.86. So now looking at this though, is it going to be positive or negative? Yes. So whenever we do square roots, we always forget the plus or minus, right? So here it's going to be minus because it is falling back down towards the earth, meaning it has a negative in front of it. So what's next? Well, how do we do that? Because we have the velocity of delta x, or velocity of x. So before we get there, do what?
Time independent.
What's the time independent one for x? Or what is the time independent equation?
Squared equals the initial square equals to x.
Okay. So the problem with this equation, what's our acceleration in the x direction? Anything times 0, 0, right? So this equation just simply says and proves that our final velocity is equal to our initial velocity. Does that make sense? So can't use that. So what's another equation we could use to find our delta x? Okay. So before we go over to the X stuff, we can use an equation to find the time, because once we have the time, we can find our delta X. So the equation we're going to use for that is going to be our final velocity of Y that we just found is equal to our initial velocity of Y plus A of Y times T. Quickly rearrange it to Vy minus V naught Y over A sub Y is equal to T. Anybody confused how that just happened? And what do we wind up for our time? Good. Anybody on Zoom? Nobody? So did you do negative 3.86 minus parentheses 3.7 sine 41 over negative 9.8? McDonald? Okay. That's what happened there. Because I too got the T is equal to 0.642 seconds. Okay, now what? So the next equation we're going to use is really the only equation you can use for the X direction is delta X is equal to V naught of X or V of X. It doesn't really matter if you have that naught there or not, times T, which if you look at it, what is it rearranged? What equation is that identical to? It's identical to our velocity, which is velocity is equal to delta X times T. Just multiply both sides by T. So our delta X is equal to the 3.7 cosine of 41 times 0.642. Which gives us delta X is equal to what? X is equal to 1.79 meters. And that is probably one of the longest problems you will have to work. I don't even know if he'll give you one that long for the test, but if you know how to work that out, then you're pretty set for anything in 2 dimensions. So finally, we have a raindrop falling vertically at 6.1 meters per second. What angle from the vertical do they make for a person jogging at 1.59 meters per second? So, like I said earlier, this one is actually not asking for anything in the horizontal, which actually, whenever I had this problem, I missed it because I did it from the horizontal. I didn't read properly. So we're actually looking for theta here and not from here like normal, which would throw people off, which is why she did this problem for us. So we know our y is 6.1 meters per second. And I know we are running at 1.59 meters per second. What do we do? How do we find theta? So TOA again. Tangent of theta is equal to our opposite over adjacent. Theta is equal to tan inverse of -1 for opposite over adjacent. Meaning the tangent inverse of what over what? What's on top? .59 over 6.1. Meaning theta equals what? 14.6. 14.6 degrees. Any questions? Okay, if there's no questions, I do need to run to the restroom real quick. So we'll take a 3 to 5 minute break. Stretch your legs. Walk away for a second if you need to. I'll be back.
So an exoplanet has twice the mass and 1/4 of the radius of the Earth. Find the acceleration due to gravity on its surface in terms of g, the acceleration of gravity on Earth's surface. So this is us getting into forces. They're complicated and I don't really like, but they're a vital part of physics. So let's figure these out. So y'all know the equation we're going to use for this. So the equation we're going to use is gravity for that planet, said planet, is equal to big G so we know this, and we know that our planet, Earth, is equal to big G as well. Mass of Earth over radius of Earth. Right? So whenever we set these equal to each other, we we get gravity of the planet is equal to mass of the planet over mass of the Earth divided by radius of the planet divided by radius of Earth squared, which then is equal to 2 5. Whenever we do that, we know it's going to be 32. Because 0.25 squared is 1/8. Multiply that by 8. Multiply bottom and top by 8. Actually, not 16. So 16 times 2 is 32. Anybody confused as to how we got to 32 G's? I just plug in 2 divided by 0.25 squared is 32. Next, a protest, not a pretest, protest against the umpire's call. A baseball pitcher throws a ball straight up in the air at a speed of 17 meters per second. Process, he moves his hand for a distance of 1.4 meters. The ball has a mass of 0.15 kilograms. Find the force he exerts on the ball to give it this upward speed. So what's first?
Sure.
So we got ball. It's got to force something. Goes in the air, falls down. So whenever he moves his hand, 1.4 meters. And we know we have a mass. So now that we got it drawn out, write it out. V naught is equal to 17 meters per second. Delta x is going to be equal to 1.4 our mass. Hear me very well, somewhat. Is it better here like this? A little bit better.
How about that? Is that better? Okay. Awesome. So we know the mass is 0.15 kilograms. So what do we have to find first to find force? What's our equation for force? Yes. So force is equal to mass times acceleration, meaning we're looking for force and we're looking for acceleration. How do we find acceleration? So to find our acceleration, we're just going to use a kinematic equation, time independent. So final velocity squared is equal to initial velocity squared plus 2 times acceleration times delta x. So we know our final velocity. That's our final velocity. This is our initial velocity, is 0. At the bottom, still in hand, not moving. So final velocity is 17 squared is equal to 0 squared plus 2 times our acceleration, which we're finding, times the 1.4. So 17 squared is 289 is equal to 2.8a, divide both sides by 2.8. And we find our acceleration is what? 103 meters per second squared. So now that we have our acceleration, we can find the force applied to the ball. So you just simply plug into the equation right here. Force is equal to 0.15 times 103, giving you what for force? Sig figs? 15.5 newtons. Any questions? Okay, now this is a fun problem to work through. So we have a traffic light hanging by 2 cables, and we are going to find the resultant force exerted on the 2 cables supporting the traffic light in a figure. What's first? So in this, first thing I like to do, I like to draw it out. So we have a little triangle. I don't like that triangle. And then we find components. So we know this angle is 45 degrees. No, this angle is 45 degrees. So what's going to be our horizontal component? So our horizontal is going to be 60. Do what?
84.5. No, for some reason I didn't find that.
Cosine 45. Because it is a 45-degree angle, though, our cosine and sine should be the same, right? So Just label all your components. Okay, now the equation we're going to use is going to be f of y equals force sine of theta. So because the force is going to be coming straight down, we're just going to find the y component. So because there are 2 ropes, we'll also multiply it by 2. So 60 sine of 45 times 2 will give you the force exerted by the 2 cables. Which you had. So when we plug that in, we're going to find that the force is equal to 84.9 newtons.
If they weren't right triangles, would it be like F sine theta times F sine phi?
So you're talking,
If like the angles were asymmetrical.
so say like this was 20 and this was 40,
Yeah.
you would still have a right triangle just by drawing your line. Because right triangles are good. We know how to work those. So doing that would be pretty, just make sure it's a right triangle. They're easy to work with. You can take very asymmetrical triangles that are side by side and then like just work them to get right triangles. It makes your life a lot easier because I don't know how to work on right triangles. So I didn't take trig, so I'm happy about it. So now, because we did find the force in the y direction, the weight of the light is going to be 84.9 newtons. Because weight is equal to force in the y direction. And then the reason we didn't do anything with the 60 cosine 45 is because of the vectors are in opposite directions, so they cancel out. Does that make sense? Because to find the overall force is f of x plus f of y. But we knew going in 2 separate directions, x is going to equal 0. So just find f of y. Any questions? Okay, if there's no questions, I will end the session. Oh, we only have one more. I bet we could get it done. I thought I had a couple more. Okay. So what do we do? How do we start? A boy coasts down a hill on a sled, reaching a level surface at the bottom with a speed of 6.5 meters per second. The coefficient of friction between the sled's runner and snow is 0.04. The boy and sled weigh 650 newtons. How far does the sled travel on the surface before coming to a rest? So first, draw it out. Draw it out, label it, make it a free body diagram. That's the word I was looking for. So we go down a hill, then we find a level surface, level-ish surface, I guess. Cracks aren't really level, so we have our little particle down here. Mg is equal to 650. We also have the normal force coming up at 650 newtons. We have our little coefficient of friction is 0.04. Our speed is 65 or 6.5 meters per second. And that's what we know. We're looking for whenever our velocity is equal to 0 meters per second. So we're looking for our delta x. So now we can write down everything. Mg is equal to 650 newtons. Our mu is equal to 0.040. Initial velocity is 6.5 meters per second. Our delta x is what we're looking for. And our final velocity is 0. So f of k is equal to mu times n. Our normal force times mu gives us kinetic friction or kinetic force, which is 0.04 times 650, which gives us 26 newtons. We also know that F of K is equal to force, which is equal to mass times acceleration, right? Before we can go into that, we have to figure out what they weigh in mass. So we know weight is equal to mg. We know the weight is 650 times m times 9.8. Divide both sides by 9.8. We find out that mass is 66.3. So we set that 26 is equal to 66.3 times acceleration. Divide both sides by 66.3. Our acceleration is 0.392. We also know that they're slowing down, so it's going to be negative. Have I lost anybody yet? That negative actually comes from up here, comes with the negative 26, because 0.04 is pointing back in the negative direction. Okay, now that we're this far, kinematics. They don't ever leave you alone, I promise. So the equation we use is final velocity squared is equal to v naught squared plus 2a delta x. Final velocity is 0. Initial velocity is 6.5 squared plus 2 times negative 0.392 times delta x whenever we move the 6.5 squared over, it turns into negative 42.25. Those multiplied together is negative 0.784 times delta x. Divide both sides, leaving us with a delta x of 53.9 meters. I know I went really fast there. Are there any questions over this?
Similar to the question I was gonna have you go over. So.
Oh,
Okay.
anybody on Zoom? I know that went really fast. It was working, didn't plug it into the calculator. I'm sure y'all are still working it out. If you've got questions, let me know. Getting all your scheduling stuff figured out for next semester.
Yeah, kind of a hassle though.
I started that this morning and I don't like doing it. It stresses me out.
And then all the PT schools, which is what I might want to do in the future, they changed their prerequisites for math. So now I'm gonna have to go to JUCO over the summer to take algebra. 'Cause it used to be pre-calc.
Well, if y'all don't have any questions, I'm going to end the session. Good luck on Monday. Y'all got this. Here we go.